Welcome to the AIM. This is one of the longer manuals from the FAA that you will need to learn for your sport or private pilot's license. Thank you for watching. Please subscribe for YouTube's algorithms so more of the content will reach a larger aviation community. Also, there is additional content available by subscribing to Patreon. I added some deadpan jokes and some actual crash investigations to try and make this material a little bit easier to digest. Please leave a comment if you liked it. If you have any questions, ask your flight instructor. Outline of the AIM, Chapter 1. Air Navigation, Section 1. Navigation Aids, Section 2. Performance-based navigation and area navigation. Chapter 2. Aeronautical lighting and other airport visual aids. Section 1. Airport lighting aids. Section 2. Air navigation and obstruction lighting. Section 3. Airport marking aids and signs. Chapter 3. Airspace. Section 1. General. Section 2. Controlled airspace. Section 3. Class G airspace. Section 4. Special use airspace. Section 5, Other Airspace Areas, Chapter 4, Air Traffic Control, Section 1, Services Available to Pilots, Section 2, Radio Communications Phraseology and Techniques, Section 3, Airport Operations, Section 4, ATC Clearances and Aircraft Separation, Section 5, Surveillance Systems, Section 6, Operational Policy Procedures for Reduced Vertical Separation Minimum, in the domestic U.S., Alaska, offshore airspace, and the San Juan Fur. Section 7, Operational Policy Procedures for the Gulf of America 50 nm Lateral Separation Initiative. Chapter 5, Air Traffic Procedures. Section 1, Pre-Flight. Section 2, Departure Procedures. Section 3, En Route Procedures. Section 4, Arrival Procedures. Section 5, Pilot Controller Roles and Responsibilities. Section 6, National Security and Interception Procedures. Chapter 6, Emergency Procedures. Section 1, General. Section 2, Emergency Services Available to Pilots. Section 3, Distress and Urgency Procedures. Section 4, Two-Way Radio Communications Failure. Section 5, Aircraft Rescue and Firefighting Communications. Chapter 7, Safety of Flight. Section 1, Meteorology. Section 2, Barometric Altimeter Errors and Setting Procedures. Section 3, Cold Temperature Barometric Altimeter Errors, Setting Procedures and Cold Temperature Airports. Section 4, Wake Turbulence. Section 5, Bird Hazards and Flight over National Refuges, Parks, and Forests. Section 6, Potential Flight Hazards. Section 7, Safety, Accident, and Hazard Reports. Chapter 8, Medical Facts for Pilots. Section 1, Fitness for Flight. Chapter 9, Aeronautical Charts and Related Publications. Section 1, Types of Charts Available. Chapter 10, Helicopter Operations. Section 1, Helicopter IFR Operations. Section 2, Special Operations. Chapter 1, Air Navigation. Section 1, Navigation Aids. Source text is reproduced word for word from the FAA Aeronautical Information Manual 111, General. The next section is General. Here's a summary from AMP Aviation. The FAA doesn't own every NAVAID out there, but it does own the rulebook for using them on an instrument flight. And when a NOTAM says a beacon is down, your displays don't get a vote. Trust the NOTAM. 1. Various types of air navigation aids are in use today, each serving a special purpose. These aids have varied owners and operators, namely the Federal Aviation Administration, the military services, private organizations, individual states, and foreign governments. The FAA has the statutory authority to establish, operate facilities, and to prescribe standards for the operation of any of these aids which are used for instrument flight in federally controlled airspace. These aids are tabulated in the chart supplement. 2. Pilots should be aware of the possibility of momentary erroneous indications on cockpit displays when the primary signal generator for a ground-based navigational transmitter is inoperative. Pilots should disregard any navigation indication, regardless of its apparent validity, if the particular transmitter was identified by NOTAM or otherwise as unusable or inoperative. Practical application for GA pilots. Check NOTAMs for every NAVAID along your route before you fly, not just at your destination. If a VOR, ILS, or beacon is flagged out of service, don't treat a plausible-looking in-flight indication as proof it's back. A little levity. Why did the student pilot bring a highlighter to the NOTAM briefing? Because unusable or inoperative is not a font, it's a warning. 112. Non-directional radio beacon. The next section is non-directional radio beacon. Here's a summary from AMP Aviation. NDBs are the old-timers of the NAVAID world, simple, cheap, and easily upset by weather and static. If your ADF needle starts twitching, that's your cue to double check, not double down. 1. A low or medium frequency radio beacon transmits non-directional signals, whereby the pilot of an aircraft, properly equipped, can determine bearings and home on the station. These facilities normally operate in a frequency band of 190 to 535 kHz, according to ICAO Annex 10, the frequency. Range for NDBS is between 190 and 1,750 kHz, and transmit a continuous carrier with either 400 or 1020 Hz modulation. All radio beacons except the compass locators transmit a continuous 3-letter identification and code except during voice transmissions. 2. When a radio beacon is used in conjunction with the instrument landing system markers, it is called a compass locator. 3. Voice transmissions are made on radio beacons unless the letter W is included in the class designator. 4. Radio beacons are subject to disturbances that may result in erroneous bearing information. Such disturbances result from such factors as lightning, precipitation, static, etc. At night, radio beacons are vulnerable to interference from distant stations. Nearly all disturbances which affect the automatic direction finder bearing also affect the facility's identification. Noisy identification usually occurs when the ADF needle is erratic. Voice, music, or erroneous identification may be heard when a steady false bearing is being displayed. Since ADF receivers do not have a flag to warn the pilot when erroneous bearing information is being displayed, the pilot should continuously monitor the NDB's identification. Practical application for GA pilots: if you still fly behind an ADF, keep listening to the Morse identifier throughout the approach or leg, not just once at the start. A steady but wrong bearing looks exactly like a good one until you check the ID. A little levity: why did the ADF needle refuse therapy? It said it was fine, it was just going through a phase. 113. VHF omnidirectional range. The next section is VHF omnidirectional range. Here is a summary from AMP Aviation. The VOR is the reliable pickup truck of navigation, not flashy, occasionally rough running, but it'll get you to Amman Airport when GPS won't. 1. VORs operate within the 108 to 117.95 MHz frequency band and have a power output necessary to provide coverage within their assigned operational service volume. They are subject to line-of-sight restrictions, and the range varies proportionally to the altitude of the receiving equipment. Note: normal service ranges for the various classes of VORs are given in evade service volumes, paragraph 118. 2. Most VORs are equipped for voice transmission on the VOR frequency. VORs without voice capability are indicated by the letter W included in the class designator. 3. The only positive method of identifying a VOR is by its Morse code identification or by the recorded automatic voice identification, which is always indicated by use of the word VOR following the range's name. Reliance on determining the identification of an omnirange should never be placed on listening to voice transmissions by the flight service station involved. Many FSSS remotely operate several omniranges with different names. In some cases, none of the VORs have the name of the parent FSS. During periods of maintenance, the facility may radiate a TEST code, or the code may be removed. Some VOR equipment decodes the identifier and displays it to the pilot for verification to charts, while other equipment simply displays the expected identifier from a database to aid in verification to the audio tones. You should be familiar with your equipment and use it appropriately. If your equipment automatically decodes the identifier, it is not necessary to listen to the audio identification. 4. Voice identification has been added to numerous VORs. The transmission consists of a voice announcement Airville VOR alternating with the usual Morse code identification. 5. The effectiveness of the VOR depends upon proper use and adjustment of both ground and airborne equipment. Accuracy. The accuracy of course alignment of the VOR is excellent, being generally plus or minus 1 degree. Roughness. On some VORs, minor course roughness may be observed, evidenced by coarse needle or brief flag alarm activity. At a few stations, usually in mountainous terrain, the pilot may occasionally observe a brief coarse needle oscillation, similar to the indication of approaching station. Pilots flying over unfamiliar routes are cautioned to be on the alert for these vagaries, and in particular to use the to from indicator to determine positive station passage. Certain propeller revolutions per minute settings or helicopter rotor speeds can cause the VOR course deviation indicator to fluctuate as much as plus or minus 6 degrees. Slight changes to the RPM setting will normally smooth out this roughness. Pilots are urged to check for this modulation phenomenon prior to reporting a VOR station or aircraft equipment for unsatisfactory operation. A little levity: a VOR walks into a bar with a VORTAC. The bartender asks what they're having. The VOR says, "I'll take a course, plus or minus 1 degree." 6. The VOR minimum operational network. As flight procedures and route structure based on VORs are gradually being replaced with performance-based navigation procedures, the FAA is removing selected VORs from service. PBN procedures are primarily enabled by GPS and its augmentation systems, collectively referred to as Global Navigation Satellite System. Aircraft that carry DME equipment can also use RNAV, which provides a backup to continue flying PBN during a GNSS disruption. For those aircraft that do not carry DME, the FAA is retaining a limited network of VORs called the VAR-MON to provide a basic conventional navigation service for operators to use if GNSS becomes unavailable. During a GNSS disruption, the MON will enable aircraft to navigate through the affected area or to a safe landing at a MON airport without reliance on GNSS. Navigation using the MON will not be as efficient as the new PBN route structure, but use of the MON will provide nearly continuous VOR signal coverage at 5,000 feet AGL across the NAS, outside of the western U.S. mountainous area. Note, there is no plan to change the navigate and route structure in the WSMA. The VOR-MON has been retained principally for IFR aircraft that are not equipped with DME avionics. However, VFR aircraft may use the MON as desired. Aircraft equipped with DME navigation systems would, in most cases, use DME to continue flight using RNAV to their destination. However, these aircraft may, of course, use the MON. Distance to a MON airport, the VOR-MON will ensure that regardless of an aircraft's position in the contiguous United States, a MON airport will be within 100 nautical miles. These airports are referred to as MON airports and will have an ILS approach or a VOR approach if an ILS is not available. VORs to support these approaches will be retained in the VOR-MON. MON airports are charted on low altitude on route charts and are contained in the Chart Supplement US and other appropriate publications. Note:
any suitable airport can be used to land in the event of a VOR outage. Navigating to an airport, the VOR-MON will retain sufficient VARs and increase VOR service volume to ensure that pilots will have nearly continuous signal reception of a VOR when flying at 5,000 feet AGL. A key concept of the MON is to ensure that an aircraft will always be within 100 nautical miles of an airport with an instrument approach that is not dependent on GPS. If the pilot encounters a GPS outage, the pilot will be able to proceed via VOR-to-VOR navigation at 5,000 feet AGL through the GPS outage area or to a safe landing at a MON airport or another suitable airport as appropriate. Nearly all VORs inside of the WSMA and outside the CONUS are being retained. Using the VOR-MON in the case of a planned GPS outage, pilots may plan to fly through the outage using the MON as appropriate and as cleared by ATC. In the case of an unscheduled GPS outage, pilots and ATC will need to coordinate the best outcome for all aircraft. The VOR-MON is a reversionary service provided by the FAA for use by aircraft that are unable to continue RNAV during a GPS disruption. The FAA has not mandated that pre-flight or in-flight planning include provisions for GPS or WAS-equipped aircraft to carry sufficient fuel to proceed to a MON airport in case of an unforeseen GPS outage. WAS users flying under Part 91 are not required to carry VOR avionics and do not have the ability or requirement to use the VOR-MON. Prudent flight planning by these WAS-only aircraft should consider the possibility of a GPS outage. Practical application for GA pilots: even if you fly GPS direct everywhere, keep VOR proficiency current. If GPS goes down, the MON is designed to keep a suitable airport within 100 nautical miles of you, but only if you can still fly a VOR radial when asked. Relevant NTSB case: on March 9, 2021, a Cessna 170 pilot near Poplar Bluff, Missouri, became lost on a cross-country flight. The airplane had no VOR equipment, and although the pilot carried a handheld GPS, he chose to navigate by dead reckoning and a phone map app instead. When the phone's battery died about 15 to 20 minutes from the destination, the handheld GPS also failed to power on. Unable to locate the airport, the pilot made a precautionary off-airport landing in a field with soft terrain, and the airplane nosed over. The NTSB's probable cause was the pilot's decision to land in a field with soft terrain, with the lack of a paper sectional chart cited as a contributing factor. The lesson for GA pilots: a single method of navigation, with no independent backup that doesn't rely on the same battery, is a gap that shows up exactly when you can least afford it. 114. VOR receiver check. The next section is VOR receiver check. Here is a summary from AMP Aviation. Your VOR receiver is a certified instrument, which means it needs a checkup. The FAA gives you 5 different ways to prove yours is honest. 1. The FAA VOR test facility transmits a test signal which provides users a convenient means to determine the operational status and accuracy of a VOR receiver while on the ground where a VOT is located. The airborne use of VOT is permitted, however, its use is strictly limited to those areas' altitude specifically authorized in the chart supplement or appropriate supplement. 2. To use the VOT service, tune in the VOT frequency on your VOR receiver. With the course deviation indicator centered, the omni-bearing selector should read 0 degrees with the 2 from indication showing from, or the omni-bearing selector should read 180 degrees with the 2 from indication showing to. Should the VOR receiver operate in RMI, it will indicate 180 degrees on any omni-bearing selector setting. 2 means of identification are used. One is a series of dots and the other is a continuous tone. Information concerning an individual test signal can be obtained from the local FSS.
3. Periodic VOR receiver calibration is most important. If a receiver's automatic gain control or modulation circuit deteriorates, it is possible for it to display acceptable accuracy and sensitivity close into the VOR or VOT and display out-of-tolerance readings when located at greater distances where weaker signal areas exist. The best assurance of having an accurate receiver is periodic calibration. Yearly intervals are recommended, at which time an authorized repair facility should recalibrate the receiver to the manufacturer's specifications. 4. Federal Aviation Regulations provides for certain VOR equipment accuracy checks prior to flight under instrument flight rules. To comply with this requirement and to ensure satisfactory operation of the airborne system, the FAA has provided pilots with the following means of checking VOR receiver accuracy, a VOT or radiated test signal from an appropriately rated radio repair station, certified airborne checkpoints and airways, certified checkpoints on the airport surface, or, if an airborne checkpoint is not available, an established VOR airway, using a prominent ground point, preferably more than 20 nautical miles from the VOR ground facility, maneuvering the aircraft directly over the point at a reasonably low altitude above terrain and obstructions. 5. A radiated VOT from an appropriately rated radio repair station serves the same purpose as an FAA VOR signal, and the check is made in much the same manner as a VOT. With these differences, the frequency normally approved by the Federal Communications Commission is 108 MHz. Repair stations are not permitted to radiate the VOR test signal continuously, so the owner or operator must make arrangements with the repair station to have the test signal transmitted. A representative of the repair station must make an entry into the aircraft logbook or other permanent record certifying to the radial accuracy and the date of transmission, and it is necessary to verify which test radial is being transmitted and whether you should get a to or from indication. 6. Airborne and ground checkpoints consist of certified radials that should be received at specific points on the airport surface or over specific landmarks while airborne in the immediate vicinity of the airport. Should an error in excess of plus or minus 4 degrees be indicated through use of a ground check or plus or minus 6 degrees using the airborne check, instrument flight rules flight must not be attempted without first correcting the source of the error. Caution: no correction other than the correction card figures supplied by the manufacturer should be applied in making these VOR receiver checks. Locations of airborne checkpoints, ground checkpoints, and VOTs are published in the chart supplement. If a dual system VOR is installed in the aircraft, one system may be checked against the other. The maximum permissible variation between the two indicated bearings is 4 degrees. Practical application for GA pilots: log your VOR checks, date, error, and which method, write in the logbook or an app. It takes 30 seconds and is exactly what a ramp check or an incident investigation will ask for. A little levity: how do you know your VOR receiver failed its check ride? It keeps insisting it's from the airport when you're clearly still on the ramp. 1.1.5. Tactical Air Navigation. The next section is Tactical Air Navigation. Here's a summary from AMP Aviation. TACAN is the military's answer to VOR DME. D afferent guts, same readout for the pilot, and it's why so many VORs are actually VORTACs under the hood. 1. For reasons peculiar to military or naval operations, the Civil VOR Distance Measuring Equipment System of air navigation was considered unsuitable for military or naval use. A new navigational system, TACAN, was therefore developed by the military and naval forces to more readily lend itself to military and naval requirements. As a result, the FAA has integrated TACAN facilities with the Civil VOR DME program. Although the theoretical or technical principles of operation of TACAN equipment are quite different from those of VOR DME facilities, the end result, as far as the navigating pilot is concerned, is the same. These integrated facilities are called VORTACs. 2. TACAN ground equipment consists of either a fixed or mobile transmitting unit. The airborne unit, in conjunction with the ground unit, reduces the transmitted signal to a visual presentation of both azimuth and distance information. TACAN is a pulse system and operates in the ultra-high frequency band of frequencies. Its use requires TACAN airborne equipment and does not operate through conventional VOR equipment. Practical application for GA pilots. Civilian GA pilots without TACAN equipment can't use TACAN directly, but this is exactly why a VORTAC gives you the same VOR azimuth service you'd get from a plain VOR, no special handling needed. 1.1.6. VHF, Omnidirectional Range, Tactical Air Navigation. The next section is VORTAC. Here's a summary from AMP Aviation. 2 systems, 1 antenna farm. A VORTAC is a VOR and a TACAN sharing a site, which is why your DME reading and your VOR bearing always agree. 1. A VORTAC is a facility consisting of 2 components, VOR and TACAN, which provides 3 individual services, VOR azimuth, TACAN azimuth, and TACAN distance at one site. Although consisting of more than one component, incorporating more than one operating frequency, and using more than one antenna system, a VORTAC is considered to be a unified navigational aid. Both components of a VORTAC are envisioned as operating simultaneously and providing the three services at all times. 2. Transmitted signals of VOR and TACAN are each identified by three-letter code transmission and are interlocked so that pilots using VOR azimuth with TACAN distance can be assured that both signals being received are definitely from the same ground station. The frequency channels of the VOR and the TACAN at each VORTAC facility are paired in accordance with a national plan to simplify airborne operation. Practical application for GA pilots: when you tune a VORTAC, your DME distance and VOR bearing are guaranteed to come from the same physical station. A nice sanity check you don't get with some standalone DME setups. 1.17. Distance measuring equipment. The next section is distance measuring equipment. Here is a summary from AMP Aviation. DME is basically radar for range only. Your airplane asks a ground station how far, and gets an answer accurate to a fraction of a mile. 1. In the operation of DME, paired pulses at a specific spacing are sent out from the aircraft and are received at the ground station. The ground station then transmits paired pulses back to the aircraft at the same pulse spacing but on a different frequency. The time required for the round trip of the signal exchange is measured in the airborne DME unit and is translated into distance from the aircraft to the ground station. 2. Operating on the line of sight principle, DME furnishes distance information with a very high degree of accuracy. Reliable signals may be received at distances up to 199 nautical miles at line of sight altitude with an accuracy of better than 1/2 mile or 3% of the distance, whichever is greater. Distance information received from DME equipment is slant range distance and not actual horizontal distance. 3. Operating frequency range of a DME according to ICAO Annex 10 is from 960 MHz to 1215 MHz. Of a DME equipment will receive distance information from a VORTAC automatically, while aircraft equipped with VOR must have a separate DME airborne unit. 4. VOR DME, VORTAC, Instrument Landing System DME, and Localizer DME navigation facilities established by the FAA provide course and distance information from collocated components under a frequency pairing plan. Aircraft receiving equipment, which provides for automatic DME selection, assures reception of azimuth and distance information from a common source when designated VOR DME, VORTAC, ILS DME, and LOC DME are selected. 5. Due to the limited number of available frequencies, assignment of paired frequencies is required for certain military non-collocated VOR and TACAN facilities which serve the same area but which may be separated by distances up to a few miles. 6. VOR DME, VORTAC, ILS DME, and LOC DME facilities are identified by synchronized identifications which are transmitted on a timeshare basis. The VOR or localizer portion of the facility is identified by a coded tone modulated at 1020 Hz or a combination of code and voice. The TACAN or DME is identified by a coded tone modulated at 1350 Hz. The DME or TACAN coded identification is transmitted one time for each 3 or 4 times that the VOR or localizer coded identification is transmitted. When either the VOR or the DME is inoperative, it is important to recognize which identifier is retained for the operative facility. A single coded identification with a repetition interval of approximately 30 seconds indicates that the DME is operative. 7. Aircraft equipment which provides for automatic DME selection assures reception of azimuth and distance information from a common source when designated VOR DME, VORTAC, and ILS DME navigation facilities are selected. Pilots are cautioned to disregard any distance displays from automatically selected DME equipment when VOR or ILS facilities, which do not have the DME feature installed, are being used for position determination. Practical application for GA pilots: remember, DME gives slant range, not ground distance. Right over the station at altitude, don't be surprised the readout doesn't hit 0. A little levity: DME's favorite pickup line: are you a ground station? Because I'm getting a strong signal and I'd like to measure the distance between us. 118. NAVAID service volumes. The next section is NAVAID service volumes. Here's a summary from AMP Aviation. Every NAVAID has a 3D bubble, where the FAA promises the signal is good, fly outside it, and you're on your own for signal quality even if the needle looks fine. 1. The FAA publishes standard service volumes for most NAVAIDs. The SSV is a 3-dimensional volume within which the FAA ensures that a signal can be received with adequate signal strength and course quality and is free from interference from other NAVAIDs on similar frequencies. However, the SSV signal protection does not include potential blockage from terrain or obstructions. The SSV is principally intended for off-route navigation, such as proceeding direct to or from a VOR when not on a published instrument procedure or route. Navigation on published instrument procedures or routes. may use navaids outside of the SSV when extended service volume is approved, since adequate signal strength, course quality, and freedom from interference are verified by the FAA prior to the publishing of the instrument procedure or route. Note: a conical area directly above the navaid is generally not usable for navigation. 2. A navaid will have service volume restrictions if it does not conform to signal strength and course quality standards throughout the published SSV. Service volume restrictions are first published in notices to airmen and then with the alphabetical listing of the navaids in the chart supplement. Service volume restrictions do not generally apply to published instrument procedures or routes unless published in NOTAMs for the affected instrument procedure or route. 3. VOR-DME TACAN standard service volumes. The 3 original SSVs are designated with 3 classes of navaids: terminal, low, and high. The usable distance of the navaid depends on the altitude above the transmitter height for each class. With the progression of navigation capabilities to performance-based navigation, additional capabilities for off-route navigation are necessary. For example, the VOR-MON requires the use of VORs at 5,000 feet AGL, which is beyond the original SSV ranges, and PBN procedures using DME require extended ranges. As a result, the FAA created 4 additional SSVs, VOR low and VOR high, and DME low and DME high. In the past, navaids at one location typically all had the same SSV. A common SSV may no longer be the case at all locations. A VOR DME, for example, could have an SSV of VL for the VOR and DH for the DME. TACAN azimuth will only be classified as T, L, or H Fig.I 11 original standard service volumes. Above transmitter height, January 2nd, 1761, lower edge of the terminal service volume. April 20th, 2023, FIG111, lower edge of low and high service volumes. AIM, Fig 1-1-5, new DME service volumes. TBL1, 11 VOR, DME. TACAN standard service volumes. A little levity, a pilot asked the DME how far the service volume extended. The DME said, "It's complicated, ask me again below 12,900 feet, 119. Instrument landing system. The next section is instrument landing system. Here's a summary from AMP Aviation. The ILS is the granddaddy of precision approaches, a course beam, a glide path beam, and a chain of markers that together will fly you right down to the runway. If you fly it, not just watch it. 1. General. The ILS is designed to provide an approach path for exact alignment and descent of an aircraft on final approach to a runway. The basic components of an ILS are the localizer, glide slope, and outer marker, and, when installed for use with Category 2 or Category 3 instrument approach procedures, an inner marker. The system may be divided functionally into 3 parts: guidance information, range information, and visual information. The following means may be used to substitute for the OM: compass locator, precision approach radar, airport surveillance radar, distance measuring equipment, VOR, or non-directional beacon fixes authorized in the standard instrument approach procedure, or a suitable RNAV system with GPS, capable of fixed identification on a standard instrument approach procedure. Where a complete ILS system is installed on each end of a runway, the ILS systems are not in service simultaneously. 2. Localizer. The localizer transmitter operates on one of 40 ILS channels within the frequency range of 108.10 to 111.95 MHz, providing the pilot with course guidance to the runway centerline. The approach course of the localizer is called the front course. It is adjusted for a course width of 700 feet at the runway threshold. The course line along the extended center line of a runway in the opposite direction to the front course is called the back course. Caution: unless the aircraft's ILS equipment includes reverse sensing capability, when flying inbound on the back course it is necessary to steer the aircraft in the direction opposite the needle deflection. When making corrections from off course to on course, this flying away from the needle is also required when flying outbound on the front course. Do not use back course signals for approach unless a back course approach procedure is published for that particular runway and the approach is authorized by ATC. Identification is in International Morse code and consists of a 3-letter identifier preceded by the letter I, transmitted on the localizer frequency. The localizer provides course guidance throughout the descent path to the runway threshold from a distance of 18 nautical miles from the antenna between an altitude of 1,000 feet above the highest terrain along the course line and 4,500 feet above the elevation of the antenna site, with proper off-course. Indications provided to 10 degrees either side of the course along a radius of 18 nautical miles, and from 10 to 35 degrees either side of the course along a radius of 10 nautical miles. Unreliable signals may be received outside of these areas. ATC may clear aircraft on procedures beyond the service volume when the controller initiates the action or when the pilot requests and radar monitoring is provided. All chartered procedures with localizer coverage beyond the 18 nautical miles SSV have been through the approval process for expanded service volume and have been validated by flight inspection. TBL 1-4. GPS approval required authorized use. FIG 1-7 ILS expanded service volume. 3. Localizer type directional aid. The LDA is of comparable use and accuracy to a localizer, but is not part of a complete ILS. The LDA course usually provides a more precise approach course than the similar simplified directional facility installation, which may have a course width of 6 or 12 degrees. The LDA is not aligned with the runway. Straight-in minimums may be published where alignment does not exceed 30 degrees between the course and runway, and circling minimums only are published where this alignment exceeds 30 degrees. A very limited number of LDA approaches also incorporate a glide slope, annotated on the approach chart as LDA glide slope. These fall under approach with vertical guidance. Because the final approach course is not aligned with the runway center line, additional maneuvering will be required compared to an ILS approach. 4. Glide slope glide path. The UHF glide slope transmitter, operating within the frequency range 329.15 MHz to 325 MHz, radiates its signals in the direction of the localizer front course. Caution: false glide slope signals may exist in the area of the localizer back course approach, which can cause the glide slope flag alarm to disappear and present unreliable glide slope information. Disregard all glide slope signal indications when making a localizer back course approach unless a glide slope is specified on the approach and landing chart. The glide slope transmitter is located between 750 and 1,250 feet from the approach end of the runway and offset 250 to 650 feet from the runway centerline, transmitting a glide path beam 1.4 degrees wide vertically down to the lowest authorized decision height specified in the approved ILS approach procedure. The glide path projection angle is normally adjusted to 3 degrees above horizontal, intersecting the M&M at about 200 feet and the OM at about 1,400 feet above the runway elevation, and is normally usable to a distance of 10 nautical miles. Pilots must be alert when approaching the glide path interception, since false courses and reverse sensing will occur at angles considerably greater than the published path. Make every effort to remain on the indicated glide path. Caution: avoid flying below the glide path to assure obstacle terrain clearance is maintained. The published glide slope threshold crossing height does not represent the height of the actual glide path on course indication above the runway threshold. Pilots must be aware of the vertical height between the aircraft's glide slope antenna and the main gear in the landing configuration, and at the DH, plan to adjust the descent angle accordingly. Tests indicate a comfortable wheel crossing height is approximately 20 to 30 feet, depending on the type of aircraft. A little levity, glide slope, and localizer. Walk into a bar. The bartender asks, "What'll it be?" Localizer says, "Just keep me centered." Glide slope says, "Same, but at 3 degrees. 5. Distance measuring equipment. When installed with the ILS and specified in the approach procedure, DME may be used in lieu of the OM as a back course final approach fix, and to establish other fixes on the localizer course. In some cases, DME from a separate facility may be used within terminal instrument procedures limitations to provide ARC initial approach segments, as a FAF for BC approaches, and as a substitute for the OM. 6. Marker beacon. ILS marker beacons have a rated power output of 3 watts or less and an antenna array designed to produce an elliptical pattern with dimensions at 1,000 feet above the antenna of approximately 2,400 feet in width and 4,200 feet in length. Airborne marker beacon receivers with a selective sensitivity feature should always be operated in the low sensitivity position for proper reception of ILS marker beacons. ILS systems may have an associated OM, and M&M is no longer required, though some are still in use. Locations with a Category 2 ILS also have an inner marker, required only for Cat 2 operations that do not have a published radio altitude minimum. A back course marker normally indicates the ILS back course final approach fix or approach descent is commenced. 7. Compass locator. Compass locator transmitters are often situated at the M&M and OM sites, with a power of less than 25 watts, a range of at least 15 miles, and operating between 190 and 535 kHz. At some locations, higher-powered radio beacons up to 400 watts are used as OM compass locators. Compass locators transmit 2-letter identification groups. The outer locator transmits the first 2 letters of the localizer identification group, and the middle locator transmits the last 2 letters. 8. ILS minimums. The lowest authorized ILS minimums, with all required ground and airborne systems components operative, are Category 1, 200 Moroccan dirham feet and RVR 2,400 feet, Special Authorization Category, I 150 Moroccan dirham feet and RVR 1,400 feet, HUD to DH, Category 2, 100 Moroccan dirham feet and RVR 1,200 feet, special authorization category 2 with reduced lighting, 100 Moroccan dirham feet and RVR 1,200 feet with auto land or HUD to touchdown, category ILA, DH or DH below 100 feet and RVR not less than 700 feet and RVR, no DH or DH below 50 feet and RVR less than 700 feet but not less than 150 feet, and category ILE, no DH and no RVR limitation. Special authorization and equipment are required for categories 2 and 39. Inoperative ILS components. When the localizer fails, an ILS approach is not authorized. When the glide slope fails, the ILS reverts to a non-precision localizer approach. See the inoperative component table in the U.S. Government Terminal Procedures publication for adjustments to minimums due to inoperative airborne or ground system equipment. 10. ILS course and glide slope distortion. All pilots should be aware that ILS installations are subject to signal interference by surface vehicles and aircraft. ILS critical areas are established near each localizer and glide slope antenna, and ATC responsibilities for protecting them vary with the official weather observation. At a ceiling of 800 feet or higher and visibility 2 miles or greater, no critical area protection is provided unless requested by the flight crew. Below those values, holding below 5,000 feet between the outer marker and the airport will not be authorized, and vehicles aircraft will not be authorized in or over the localizer or glide slope critical areas when an arriving aircraft is inside the OM, with limited exceptions for preceding arrivals or departures on the same or another runway. Below a 200-foot ceiling or 2,000-foot RVR, the same protections extend from the middle marker or 1/2 mile final. Flight crews should advise the tower anytime they intend an autoland SA Cat Y, Cat 2, or Cat 3 operation when weather is at or above 800 feet and 2 miles visibility, so ATC can confirm whether critical areas are protected. Pilots are cautioned that vehicular traffic not subject to ATC may cause momentary deviation to ILS course or glide slope signals, and that critical areas are not protected at uncontrolled airports or when weather is above the values requiring protective measures. Aircraft conducting coupled or autoland operations should be especially alert and prepared to intervene. Note, unless otherwise coordinated through flight standards, ILS signals to Category 1 runways are not flight inspected below the point that is 100 feet less than the decision altitude. Guidance signal anomalies may be encountered below this altitude. Practical application for GA pilots. Hand flying or coupled to the autopilot, brief yourself on which navigation source needs to be active before the FAF, so the autopilot actually arms and captures the localizer and glide slope. Don't assume it will transition automatically. Relevant NTSB case, on January 8, 2016, an instrument-rated private pilot flying a Cirrus SR-22 near Concord, North Carolina, engaged the autopilot for a coupled ILS approach, but the airplane's automated systems had not transitioned from GPS steering mode to nav mode, so the autopilot never captured the localizer or glide slope. The airplane drifted off course, and below the glide slope, ATC canceled the approach and vectored the pilot to a nearby airport. Over the next several minutes, the pilot repeatedly mismanaged the autopilot modes during 2 more approach attempts, at one point reaching a 60-degree bank and 120-degree roll excursions, and ultimately deployed the airplane's parachute system. The airplane descended into a residential area with no injuries to the pilot or passenger. The NTSB's probable cause was the pilot's inadequate management of the airplane's automated systems. The lesson for GA pilots: know exactly which button or mode arms your autopilot for an ILS and confirm the capture before you need it. January 1st, 2010. Simplified Directional Facility. The next section is Simplified Directional Facility. Here's a summary from AMP Aviation. SDF is what you get when an ILS localizer keeps the course guidance but skips the fine print. Wider beam, no glide slope, and sometimes not even aligned with the runway. 1. The SDF provides a final approach course similar to that of the ILS localizer. It does not provide glide slope information. A clear understanding of the ILS localizer and the additional factors listed below completely describe the operational characteristics and use of the SDF. 2. The SDF transmits signals within the range of 108.10 to 111.95 MHz. 3. The approach techniques and procedures used in an SDF instrument approach are essentially the same as those employed in executing a standard localizer approach, except the SDF course may not be aligned with the runway and the course may be wider, resulting in less precision. 4. Usable off-course indications are limited to 35 degrees either side of the course center line. Instrument indications received beyond 35 degrees should be disregarded. 5. The SDF antenna may be offset from the runway center line. Because of this, the angle of convergence between the final approach course and the runway bearing should be determined by reference to the instrument approach procedure chart. This angle is generally not more than 3 degrees. However, since the approach course originates at the antenna site, an approach continued beyond the runway threshold will lead the aircraft to the SDF offset position rather than along the runway center line. 6. The SDF signal is fixed at either 6 degrees or 12 degrees as necessary to provide maximum flyability and optimum course quality. 7. Identification consists of a 3-letter identifier transmitted in Morse code on the SDF frequency. The appropriate instrument approach chart will indicate the identifier used at a particular airport. January 1, 2011. Navade identifier removal during maintenance. Practical application for GA pilots. Before flying an SDF approach, check the chart for the course to runway offset angle. The needle can be perfectly centered while you're still not tracking straight down the runway. A little levity, SDF to ILS, were basically the same, except I never learned glide slope and I might not even point at the runway. The next section is Navade identifier removal during maintenance. Here is a summary from AMP Aviation. No identifier doesn't mean no signal. It means don't trust this one right now, even if it looks fine. During periods of routine or emergency maintenance, coded identification is removed from certain FAA Navades. Removal of identification serves as a warning to pilots that the facility is officially off the air for tune-up or repair and may be unreliable even though intermittent or constant signals are received. Note: during periods of maintenance, VHF ranges may radiate a TEESC code. Note: do not attempt to fly a procedure that is NOTAMED out of service, even if the identification is present. In certain cases, the identification may be transmitted for short periods as part of the testing. Practical application for GA pilots. If a Navade's Morse identifier goes silent mid-flight, treat it as out of service immediately. Don't wait for a stronger cue. January 1, 2012. Navades with voice. The next section is Navades with voice. Here is a summary from AMP Aviation. Some Navades double as a party line to flight service. Handy, but check hours before you count on it. 1. Voice-equipped en route radio navigational aids are under the operational control of either a flight service station or an approach control facility. Facilities with two-way voice communication available are indicated in the chart supplement and aeronautical charts. 2. Unless otherwise noted on the chart, all radio navigation aids operate continuously except during shutdowns for maintenance. Hours of operation of facilities not operating continuously are annotated on charts and in the chart supplement. Practical application for GA pilots. If you're planning to raise flight service over a VOR outside normal hours, check the chart supplement first. Not every voice-equipped Navade is staffed around the clock. January 1, 2013. User reports requested on Navade outages. The next section is user reports requested on Navade outages. Here is a summary from AMP Aviation. Ground monitors don't catch everything. The FAA is explicitly asking pilots to be the sensor network when a Navade or GPS starts acting weird. 1. Users of the National Airspace System can render valuable assistance in the early correction of Navade malfunctions or GNSS problems and are encouraged to report their observations of undesirable avionics performance. Although Navades are monitored by electronic detectors, adverse effects of electronic interference, new obstructions, or changes in terrain near the Navade can exist without detection by the ground monitors. Some of the characteristics of malfunction or deteriorating performance which should be reported are erratic course or bearing indications, intermittent or full flag alarm, garbled, missing or obviously improper coded identification, poor quality communications reception, or in the case of frequency interference, an audible hum or tone accompanying radio communications, or Navade identification. GNSS problems are often characterized by navigation degradation or service loss indications. Pilots conducting operations in areas where there is GNSS interference may be unable to use GPS for navigation, and ADS-B may be unavailable for surveillance. 2. Malfunctioning, faulty, inappropriately installed, operated, or modified GPS re-radiator systems intended to be used for aircraft maintenance activities have resulted in unintentional disruption of aviation GPS receivers. This type of disruption could result in unflagged, erroneous position information output to primary flight displays indicators and to other aircraft and air traffic control systems. Since receiver autonomous integrity monitoring is only partially effective against this type of disruption, the pilot may not be aware of any erroneous navigation indications. ATC may be the only means available to identify these disruptions and detect unexpected aircraft positions while monitoring aircraft for IFR separation. 3. Pilots encountering navigation error events should transition to another source of navigation and request amended clearances from ATC as necessary. 4. Pilots are encouraged to submit detailed reports of Navade or GPS anomaly as soon as practical. Pilot reports of navigation error events should contain date and time the anomaly was observed, and Navade ID, location of the aircraft when the anomaly started and ended, heading, altitude, type of aircraft, type of avionics receivers in use, number of satellites being tracked, if applicable, description of the anomaly and duration, consequences, operational impacts, actions taken to mitigate the anomaly and/or remedy provided by ATC, and post-flight pilot Maintenance actions taken. 5. Pilots operating an aircraft in controlled airspace under IFR shall comply with 14 CFR Section 91.187 and promptly report, as soon as practical, to ATC any malfunctions of navigational equipment occurring in flight. Initial reports should be submitted immediately by radio to the controlling ATC facility or FSS, or by telephone to the nearest ATC facility controlling the affected airspace. GPS problems should also be reported, post-flight, via the GPS anomaly reporting form. 6. To minimize ATC workload, GPS anomalies associated with known testing NOTAMs should not be reported in flight to ATC in detail, except when GPS degradation is experienced outside the NOTAM area, or the pilot observes unexpected consequences such as equipment failure, suspected spoofing, or failure of unexpected aircraft systems such as TAWs. Practical application for GA pilots: if a nav8 or GPS anomaly costs you time, altitude, or missed approach, file the pilot report the same day while the details are fresh. That's the data the FAA uses to catch problems ground monitors miss. Relevant NTSB case: on the night of January 6, 2006, a Piper PA-34 on a Part 135 air taxi flight near Burlington, Washington was cleared for an NDB approach in low ceilings and reduced visibility. Shortly after reporting procedure, turn inbound, radio and radar contact was lost. The wreckage was found the next morning in wooded terrain about 0.6 of a mile from the runway threshold, well short of the approach's minimum descent altitude for a straight-in landing. No mechanical malfunction was found. While this was a commercial flight rather than a personal one, the lesson applies directly to GA instrument pilots. An older, lower fidelity nav8 like an NDB leaves very little margin for a bearing or altitude error, which is exactly the kind of anomaly this paragraph asks pilots to catch and report before it becomes a habit. January 1st, 2014, Loran. The next section is Loran. Here is a summary from AMP Aviation. This one's short because Loran itself is gone. The Coast Guard pulled the plug back in 2010. Note: in accordance with the 2010 DHS Appropriations Act, the U.S. Coast Guard terminated the transmission of all U.S. Loran-C signals on February 8, 2010. The USCG also terminated the transmission of the Russian-American signals on August 1, 2010, and the Canadian Loran-C signals on August 3, 2010. Operators should also note that TSOC-60B, airborne area navigation equipment using Loran-C inputs, has been canceled by the FAA. Practical application for GA pilots: if you're flying a vintage panel with a Loran receiver still installed, treat it as decoration. The signal it needs has been off the air since 2010. A little levity: Loran's dating profile, looking for someone reliable. Status: it's complicated. Actually, status: off since 2010. January 1st, 2015, Inertial Reference Unit, Inertial Navigation System, and Attitude Heading Reference System. The next section is IRU, INS, and AHRs. Here's a summary from AMP Aviation. These systems figure out where you are by feeling every wiggle since your last known position. Accurate at first, then slowly, quietly wrong. 1. IRS are self-contained systems comprised of gyros and accelerometers that provide aircraft attitude, position, and velocity information in response to signals resulting from inertial effects on system components. Once aligned with a known position, IRS continuously calculate position and velocity. IRU position accuracy decays with time. This degradation is known as drift. 2. NSS combine the components of an IRU with an internal navigation computer. By programming a series of waypoints, these systems will navigate along a predetermined track. 3. HRs are electronic devices that provide attitude information to aircraft systems, such as weather radar and autopilot, but do not directly compute position information. 4. Aircraft equipped with slaved compass systems may be susceptible to heading errors caused by exposure to magnetic field disturbances found in materials that are commonly located on the surface or buried under taxiways and ramps. These materials generate a magnetic flux field that can be sensed by the aircraft's compass system flux detector, or gate, which can cause the aircraft system to align with the material's magnetic field rather than the Earth's natural magnetic field. The system's erroneous heading may not self-correct. Prior to takeoff, pilots should be aware that a heading misalignment may have occurred during taxi. Pilots are encouraged to follow the manufacturer's or other appropriate procedures to correct possible heading misalignment before takeoff is commenced. Practical application for GA pilots: if your slaved heading looks off right after taxi, run your compass alignment or heading correction procedure before you accept an IFR clearance based on it. January 1st, 2016, Doppler radar. The next section is Doppler radar. Here's a summary from AMP Aviation. Doppler radar is dead reckoning with a radar assist. Good, but it still needs a real position update now and then to stay honest. Doppler radar is a semi-automatic, self-contained, dead reckoning navigation system which is not continuously dependent on information derived from ground-based or external aids. The system employs radar signals to detect and measure ground speed and drift angle, using the aircraft compass system as its directional reference. Doppler is less accurate than INS, however, and the use of an external reference is required for periodic updates if acceptable position accuracy is to be achieved on long-range flights. Practical application for GA pilots, Doppler-equipped GA operations still need an outside position fix periodically. Don't trust it uncorrected for a long leg. January 1st, 2017. Global Positioning System. The next section is Global Positioning System. Here is a summary from AMP Aviation. GPS is the backbone of modern navigation, and this is the longest paragraph in this section for a reason. RAIM. Databases, waypoints, and missed approaches all live here. 1. System overview. The Global Positioning System is a space-based radio navigation system used to determine precise position anywhere in the world. The 24-satellite constellation is designed to ensure at least 5 satellites are always visible to a user worldwide. A minimum of 4 satellites is necessary for receivers to establish an accurate 3-dimensional position. The Department of Defense is responsible for operating the GPS satellite constellation. Receiver autonomous integrity monitoring is the capability of a GPS receiver to perform integrity monitoring on itself by ensuring available satellite signals meet the integrity requirements for a given phase of flight. Without RAIM, the pilot has no assurance of the GPS position integrity, and this fault detection is critical for performance-based navigation because delays of up to 2 hours can occur before an erroneous satellite transmission is detected and corrected by the satellite control segment. RAIM requires a minimum of 5 satellites, or 4 satellites and barometric altimeter input, to detect an integrity anomaly. There are generally 2 types of RAIM fault messages, one indicating there are not enough satellites available for integrity monitoring, and one indicating the RAIM integrity monitor has detected a potential error. Selective availability, a method by which GPS accuracy was intentionally degraded, was discontinued on May 1st, 2000. 2. VFR operations. GPS navigation has become an asset to VFR pilots by providing increased navigational capabilities and enhanced situational awareness, but care must be exercised to ensure that system capabilities are not exceeded. VFR pilots should integrate GPS navigation with pilotage and dead reckoning. VFR GPS panel mount receivers and handheld units have no RAIM alerting capability, which prevents the pilot from being alerted to the loss of the required number of satellites in view or a position error. Pilots should use a systematic cross-check with other navigation techniques to verify position. Databases must be updated for IFR operations and should be updated for all other operations, though there is no requirement for VFR databases to be current. Antenna location matters. Handheld GPS receivers with suction cup cockpit antennas rarely have a clear view of all available satellites, which, coupled with a lack of RAIM capability, could present erroneous position and navigation information with no warning to the pilot. Do not solely rely on GPS for VFR navigation. VFR GPS receivers should be used in conjunction with other forms of navigation, and pilots should minimize head-down time by keeping eyes outside, scanning for traffic, terrain, and obstacles. 3. IFR use of GPS. General requirements. Authorization to conduct any GPS operation under IFR requires GPS navigation equipment approved under the applicable technical standard order and installed per AC 2138 VFR, and handheld GPS systems are not authorized for IFR navigation, instrument approaches, or as a principal instrument flight reference. Aircraft using UN augmented GPS for navigation under IFR must be equipped with an alternate approved and operational means of navigation suitable for the proposed route. Active monitoring of that alternate means is required when GPS RAIM capability is lost. Procedures must be established for a predicted loss of RAIM capability, rely on other approved navigation equipment, reroute to where RAIM is available, delay departure, or cancel the flight. Aircraft navigating by IFR approved GPS are considered performance-based navigation aircraft and must file the appropriate equipment suffix. If GPS avionics become inoperative, the pilot should advise ATC and amend the equipment suffix. Prior to any GPS IFR operation, the pilot must review appropriate NOTAMs and aeronautical information. 4. Database requirements. The onboard navigation data must be current and appropriate for the region of intended operation. All approach procedures to be flown must be retrievable from the current airborne navigation database by name, not manually entered as a series of waypoints. Manual entry using latitude, longitude, or place bearing is not permitted for approach procedures. Before using a database procedure or waypoint, the pilot should verify database validity, pre-flight, confirm the database issuance, and expiration dates, and that no notice limits the specific waypoint or procedure. In flight, confirm that waypoint and transition names match the procedure chart exactly, and that waypoints are logical in location, order, and orientation, both laterally and vertically. If a cursory check indicates a potential error, do not use the retrieved procedure or waypoint until full conformity with the published data is verified. A little levity, a GPS satellite, a VOR, and an ADF needle are having a reunion. The GPS says, "I can pinpoint us to a few meters." The VOR says, "I can get us within a degree." The ADF just spins in a circle and says, "Close enough." 5. Oceanic, domestic, en route, and terminal area operations. GPS IFR operations in oceanic areas require approved avionics meeting specific equipment classes and may substitute for another approved means of long-range navigation, such as dual INS. Domestic en route and terminal IFR operations likewise require approved avionics, with the ground-based facilities appropriate for the route and any required alternate installed and operational when using non-WAAS receivers. In Alaska, GPS en route IFR operations may be conducted outside the service volume of ground-based navaids. When a GPS WAAS system is installed and operating, aircraft may operate on GNSSQ routes with GPS while remaining in ATC radar surveillance, or with GPS WAAS without that requirement, and may only operate on GNSST routes with GPS WAAS equipment. GPS IFR approach-departure operations require approved avionics of the appropriate class, a procedure retrievable by name from the current airborne navigation database, and are limited to U.S. airspace unless expressly authorized otherwise. 6. GPS instrument approach procedures. GPS overlay approaches are non-precision approaches. Pilots are authorized to fly using GPS avionics identified by or GPS in the procedure title. Localizer, LDA, and SDF procedures are not authorized as overlays. Standalone approach procedures designed specifically for GPS, with GPS in the title, have replaced many original overlays. Pilots cleared for an RNAV approach should fly the full approach from an initial approach, waypoint, or feeder fix. Randomly joining at an intermediate fix does not assure terrain clearance. GPS receivers give an arm enunciation 30 nautical miles from the airport reference point, and CDI RAIM sensitivity transitions from en route to terminal and then to approach sensitivity approaching the final approach waypoint. Do not attempt to fly an approach unless the procedure in the onboard database is current and identified as GPS on the approach chart. 7. Missed approach. A GPS missed approach requires pilot action to sequence the receiver past the missed approach waypoint to the missed approach portion of the procedure. Activating the missed approach prior to the MAWP will cause CDI sensitivity to change to terminal sensitivity, but the receiver will not sequence past the MAWP, and turns should not begin prior to it. 8. Receiver autonomous integrity monitoring. RAIM outages may occur due to an insufficient number of satellites or unsuitable satellite geometry. Prior experience with an airport does not guarantee reception at all times, and RAIM availability should always be checked. Civilian pilots may obtain GPS RAIM availability using a manufacturer-supplied prediction tool or the FAA's Service Availability Prediction Tool, or by requesting RAIM information from a flight service station during pre-flight briefings. If RAIM is not available, use another type of navigation and approach system. Select another route or destination, or delay the trip until RAIM is predicted to be available. If a RAIM failure status enunciation occurs prior to the final approach waypoint, the approach should not be completed. The pilot must proceed to the missed approach waypoint via the final approach waypoint, perform a missed approach, and contact ATC as soon as practical. If the enunciation appears after the final approach waypoint, the pilot should initiate a climb and execute the missed approach. 9. GPS familiarization. Pilots should practice GPS approaches in visual meteorological conditions until thoroughly proficient with all aspects of their equipment prior to attempting flight in instrument meteorological conditions, including using the RAIM prediction function, inserting a departure procedure. Programming and flying approaches, programming and flying direct and routed, missed approaches, entering and exiting holding patterns, and indication of the actions required for RAIM failure both before and after the final approach waypoint. Practical application for GA pilots. Before every GPS or RNAV approach, run a RAIM prediction for your ETA and confirm the receiver has sequenced from armed to approach before the FAF. If it hasn't, don't descend, fly to the missed approach point and go missed. Relevant NTSB case on December 10, 2021, a Piper PA 46500TP pilot flying solo at night near Steamboat Springs, Colorado was cleared for an RNAV approach into mountainous terrain. After passing the final approach fix but before the missed approach point, the pilot began a left turn consistent with the missed approach procedure without climbing, and the airplane struck rising terrain, killing the pilot. The NTSB's probable cause was the pilot's failure to adhere to the published instrument approach procedure, resulting in controlled flight into terrain. The lesson for GA pilots: a GPS or RNAV missed approach is not just a turn, it's a specific published climb and turn sequence, and skipping the climb is often the difference between a normal go-around and a fatal accident. January 1st, 2018. Wide Area Augmentation System. The next section is Wide Area Augmentation System. Here's a summary from AMP Aviation. WAAS is GPS with a proofreader. Ground stations and satellites. Double-check the GPS signal so your receiver can fly a glide path as tight as an ILS without any ground equipment at the airport. 1. General. The FAA developed ways to improve the accuracy, integrity, and availability of GPS signals, allowing GPS to be used as the aviation navigation system from takeoff through approach. Precisely surveyed wide-area reference stations monitor GPS satellites to determine clock and ephemeris corrections and model ionospheric propagation effects. Each station relays data to a wide-area master station, which computes a correction message, uplink to a geostationary satellite, and broadcast on the GPS frequency. The WAAS-GEO also provides an additional pseudorange measurement, in effect an extra GPS satellite in view, improving availability, while real-time monitoring improves integrity and differential corrections improve accuracy sufficient to enable approach procedures with GPS WAAS glide paths. 2. Instrument approach capabilities. Approach procedures that provide vertical guidance but do not meet ICAO precision. Approach requirements are called approach with vertical guidance, including LNAV, VNAV, and localizer performance with vertical guidance. Properly certified WAAS receivers can fly to LPV and LNAV VNAV minima using a WAAS electronic glide path, eliminating errors introduced by barometric altimetry. LPV minima may have a decision altitude as low as 200 feet height above touchdown, with visibility minimums as low as 1/2 mile where terrain and airport infrastructure support it. A different line of minima, localizer performance, is used where terrain or obstructions do not allow LPV. It provides lateral, only guidance similar to an ILS localizer and may offer lower minima than LNAV due to a narrower obstacle clearance surface. 3. General requirements. WAAS avionics must be certified under the applicable technical standard order and installed per AC 2138. GPS WAAS operation must be conducted per the FAA-approved Aircraft Flight Manual and supplements, which state the level of approach procedure the receiver supports. Prior to GPS WAAS IFR operation, the pilot must review appropriate NOTAMs. The FAA issues NOTAMs advising the status of WAAS and level of service available, including may not be AVBL NOTAMs indicating that vertical guidance may be unavailable due to ionospheric conditions, even while lateral guidance remains available, and area-wide WAAS not available, NOTAMs indicating loss or malfunction of the WAAS system. Pilots with WAAS receivers may flight plan to use any instrument, approach procedure authorized for their avionics as the planned approach at a required alternate, subject to specific restrictions on which line of minima to use for planning purposes. 4. Flying procedures with WAAS. WAAS receivers support all basic GPS approach functions plus additional capabilities, most notably the ability to generate glide path guidance independent of ground equipment or barometric aiding. When an approach procedure is selected and active, the receiver notifies the pilot of the most accurate level of service supported by the combination of the WAAS signal, the receiver, and the selected approach. Once given, the receiver operates in this mode for the duration of the approach unless that level of service becomes unavailable, and it will not fail up to a more accurate level once the approach has been activated. Both lateral and vertical scaling for LNAV, VNAV, and LPV approaches differ from the linear scaling of basic GPS, transitioning to angular scaling similar to an ILS approaching the runway. Another feature of WAAS receivers is the ability to exclude a bad GPS signal and continue operating normally, increasing the reliability of navigation. Practical application for GA pilots: when your WAAS receiver reports the level of service before an approach, fly the minima that matches exactly what's enunciated, not what the chart's best case line offers, since the receiver won't automatically upgrade mid-approach. A little levity, WAAS to GPS. I've got your back, literally. I check your work from a satellite 36,000 kilometers up. January 1st, 2019, Ground-Based Augmentation System Landing System. The next section is GBA's landing system. Here is a summary from AMP Aviation. GLS is GPS's answer to the ILS. A ground station near the runway corrects the GPS signal locally, so you get precision guidance without a localizer or glide slope antenna. 1. A GBA's ground installation at an airport can provide localized differential augmentation to the GPS signal in space, enabling an aircraft's GLS precision approach capability. Through the GBA's service and the aircraft's GLS installation, a pilot may complete an instrument approach offering three-dimensional angular, lateral, and vertical guidance for exact alignment and descent to a runway. The operational benefits of a GLS approach are similar to the benefits of an ILS or LPV approach operation. Note, to remain consistent with international terminology, the FAA will use the term GBAs in place of the former term Local Area Augmentation System. 2. An aircraft's GLS approach capability relies on the broadcast from a GBA's ground facility installation, which includes at least 4 ground reference stations near the airport's runway, a corrections processor, and a VHF data broadcast uplink antenna. To use the GGF output and be eligible to conduct a GLS approach, the aircraft requires eligibility to conduct RNP approach operations T and must meet additional specific airworthiness requirements for a GBA's receiver intended to support GLS approach operations. 3. During a GLS instrument approach procedure, the installation of an aircraft's GLS capability provides the pilot 3-dimensional lateral and vertical navigation guidance, much like an ILS instrument approach. GBA's corrections augment the GPS signal in space by offering position corrections and enhanced integrity parameters, then transmit the actual approach path definition over the VDB uplink antenna. A single GBA's ground station can support multiple GLS approaches to 1 or more runways. 4. A GLS approach offers a unique operational service volume distinct from the traditional ILS approach service volume. Despite this, in the final approach segment, a GLS approach provides precise 3D angular lateral and vertical guidance, mimicking the precision guidance of an ILS approach. Fig 1-1-9 GLS standard approach service volume. 5. Transitions to and segments of the published GLS instrument approach procedures may rely on use of RNAV1 or RNP1 prior to an initial approach fix. Using RNP-APH procedure design criteria, the missed approach procedure for a GLS approach relies exclusively on the same missed approach criteria supporting an RNP-APH. Maneuvering the aircraft in compliance with an ATC clearance to intercept a GLS approach prior to the final approach segment, the pilot should adhere to the clearance and ensure the aircraft intercepts the extended GLS final approach course within the specified service volume, confirm the aircraft is in GLS approach mode prior to reaching the glide path intercept point, and then fly the GLS final approach segment using the same techniques used to fly an ILS final approach or an RNAV approach flown to LPV minimums. Practical application for GA pilots. GLS is currently rare outside larger commercial airports, but if you fly into one, brief the approach exactly like an ILS. The flying technique is the same, even though the guidance comes from a very different ground station. January 1st, 2020. Precision approach systems other than ILS and GLS. The next section is precision approach systems other than ILS and GLS. Here is a summary from AMP Aviation. This one's a short administrative note. Anything outside ILS and GLS needs a special, individually issued procedure. You can't just show up and fly it. 1. General. Approval and use of precision approach systems other than ILS and GLS require the issuance of special instrument approach procedures. 2. Special instrument approach procedure. Special instrument approach procedures must be issued to the aircraft operator. If pilot training, aircraft equipment, and/or aircraft performance is different than published procedures, these procedures are not distributed for general public use and are issued to an aircraft operator when the conditions for operations approval are satisfied. General aviation operators requesting approval for special procedures should contact the local Flight Standards District Office to obtain a letter of authorization. Air carrier operators requesting approval for use of special procedures should contact their Certificate Holding District Office for authorization through their operations specification. Practical application for GA pilots. If your GA operation ever needs a special instrument procedure not published for public use, that request starts with your local Flight Standards District Office. Plan for lead time, since it isn't an over-the-counter approval. A little levity, a special instrument procedure and a regular instrument procedure, both waiting at the FSDO. Only one of them has a reservation. Chapter 1, Air Navigation. Section 2, Performance-Based Navigation and Area Navigation. Source text is reproduced word for word from the FAA Aeronautical Information Manual. 121, General. The next section is General. Here's a summary from AMP Aviation. PBN is the FAA's way of saying, we don't care exactly how you navigate as long as you can prove you're accurate enough at least 95% of the time. RNAV and RNP are the two flavors, and RNP is RNAV that also grades its own homework. 1. Introduction to PBN. As air travel has evolved, methods of navigation have improved to give operators more flexibility. PBN exists under the umbrella of area navigation. The term RNAV in this context, as in procedure titles, just means area navigation, regardless of the equipment capability of the aircraft. Many operators have upgraded their systems to obtain the benefits of PBN. Within PBN, there are two main categories of navigation methods or specifications: area navigation and required navigation performance. In this context, the term RNAVX means a specific navigation specification with the specified lateral accuracy value. For an aircraft to meet the requirements of PBN, a specified RNAV or RNP accuracy must be met 95% of the flight time. RNP is a PBN system that includes onboard performance monitoring and alerting capability. PBN also introduces the concept of navigation specifications, a set of aircraft and aircrew requirements needed to support a navigation application within a defined airspace concept. For both RNP and RNAV specs, the numerical designation refers to the lateral navigation accuracy in nautical miles, which is expected to be achieved at least 95% of the flight time by the population of aircraft operating within the airspace, route, or procedure. 2. Area navigation, general. RNAV is a method of navigation that permits aircraft operation on any desired flight path within the coverage of ground or space-based navigation aids, or within the limits of the capability of self-contained aids, or a combination of these. RNAV routes and terminal procedures, including departure procedures and standard terminal arrivals, are designed with RNAV systems in mind. There are several potential advantages of RNAV routes and procedures: time and fuel savings, reduced dependence on radar vectoring, altitude and speed assignments, allowing a reduction in required ATC radio transmissions, and more efficient use of airspace. RNAV operations. RNAV procedures, such as DPS and STARS, demand strict pilot awareness and maintenance of the procedure. Centerline pilots should possess a working knowledge of their aircraft navigation system and understand the various waypoint and leg types used in RNAV procedures. A waypoint is a predetermined geographical position defined in terms of latitude-longitude coordinates, most often used to indicate a change in direction, speed, or altitude along the desired path. RNAV procedures make use of both flyover and flyby waypoints. Flyby waypoints are used when an aircraft should begin a turn to the next course prior to reaching the waypoint, while flyover waypoints are used when the aircraft must fly over the point prior to starting a turn. RNAV leg types. A leg type describes the desired path preceding, following, or between waypoints on an RNAV procedure, identified by a two-letter code describing the path and its termination point, every. Leg has a termination point and some kind of path into it. A track-to-fixed leg is intercepted and acquired as the flight track to the following waypoint. A direct-to-fixed leg is a path described by an aircraft's track from an initial area direct to the next waypoint. A course-to-fixed leg is a path that terminates at a fix with a specified course at that fix. A radius-to-fixed leg is a constant radius circular path around a defined turn center that terminates at a fix. A heading leg may be a heading to altitude, heading to DME range, or heading to manual termination. VIG 125 course-to-fixed leg type. FIG 124. Navigation issues. Pilots should be aware of their navigation system inputs, alerts, and enunciations, and consider the availability and suitability of particular sensor systems. GPS WAS operators should ensure departure and arrival airports are entered to ensure proper RAIM availability and CDI sensitivity. DME position updating depends on navigation system logic and DME facility proximity, availability, geometry, and signal masking. Unique VOR characteristics may result in less accurate values from VOR DME position updating than from GPS or DME updating. Inertial reference units and inertial navigation systems are often coupled with other navigation inputs to improve overall performance. Flight management system. An FMS is an integrated suite of sensors, receivers, and computers coupled with a navigation database that generally provides performance and RNAV guidance to displays and automatic flight control systems. Inputs can be accepted from multiple sources such as GPS, DME, VOR, LOC, and IRU applied one at a time or in combination. Some FMSs detect and isolate faulty navigation information. When appropriate signals are available, FMSs will normally rely on GPS and/or DME for position updates. DME inputs coupled with one or more IRUs are often abbreviated DD. RNAV navigation specifications. RNAV1 is typically used for DPS and STARS and appears on the charts. Aircraft must maintain a total system error of not more than 1 nautical miles for 95% of the total flight time. RNAV2 is typically used for en-route operations. T routes and Q routes are. Examples: aircraft must maintain a total system error of not more than 2 nautical miles for 95% of the total flight time. RNAV10 is typically used in oceanic operations. Practical application for GA pilots: if you fly RNAV departures or arrivals, brief which waypoints are flyby versus flyover before you launch. Mixing them up is exactly how pilots end up turning early or late on a charted procedure. Attempt to make a joke relevant to the material. A flyby waypoint and a flyover waypoint are arguing about commitment. The flyby says, "I like to start turning before things get serious." The flyover says, "I have to be right on top of it first." Why did the RNAV1 route break up with the RNAV2 route? It said, "You're just not precise enough for me. I need someone within a nautical mile % of the time." An FMS walks into a bar with a GPS, a DME, and an IRU. The bartender says, "I only serve one drink at a time." The FMS says, "That's fine, I'll just blend them." If these made you laugh, stop reading your hypoxic. 122. Required navigation performance. The next section is required navigation performance. Here's a summary from AMP Aviation. RNP is RNAV that watches its own accuracy in real time and tells you the moment it's not good enough. Think of it as area navigation with a built-in lie detector. 1. General. While both RNAV navigation specifications and RNP nav specs contain specific performance requirements, RNP is RNAV with the added requirement for onboard performance monitoring and alerting. RNP is also a statement of navigation performance necessary for operation within a defined airspace. A critical component of RNP is the ability of the aircraft navigation system to monitor its achieved navigation performance and to identify for the pilot whether the operational requirement is or is not being met during an operation. The RNP capability of an aircraft will vary depending upon the aircraft equipment and the navigation infrastructure. An aircraft may be eligible for RNP1 but not capable of RNP1 operations due to limited nav-aid coverage or avionics failure. Nav specs should be considered different from one another, not better or worse. An RNP1 eligibility does not mean automatic RNP2 or RNAV1 eligibility. The FAA requires that aircraft navigation databases hold only those procedures that the aircraft maintains eligibility for. If a specific instrument procedure can't be found in the database, it's likely the procedure contains PBN elements the aircraft is ineligible for or cannot compute and fly. 2. PBN operations, lateral accuracy values. Lateral accuracy values are applicable to a selected airspace, route, or procedure, typically expressed as a distance in nautical miles from the intended centerline. RNP APH procedures in the U.S. are titled RNAV and offer several lines of minima, LNAV, LNAV, LPV, and LP. GPS with or without a space-based augmentation system can provide the lateral information for LNAV minima. LNAV INAV incorporates lateral guidance with vertical path guidance. Pilots are required to use SBAs to fly to LPV or LP minima. RNP APH has a lateral accuracy value of 1 in the terminal and missed approach segments, scaling to RNP 0.3% in the final approach. RNP authorization required approach procedures titled RNAV in the U.S. have stringent equipage and pilot training standards and require special FAA authorization. Scalability and RF turn capability are mandatory, and lateral accuracy values can range below 1 in the terminal and missed approach segments, scaling to RNP 0.3% or lower in the final approach. RNP AR departure procedures similarly require special authorization, with lateral accuracy scaling to no lower than RNP 0.3% in the initial departure flight path. Advanced RNP is a nav spec with a minimum set of mandatory avionics functions including RF turn calculation, scalable RNP, and parallel offset flight path generation. An aircraft eligible for ARNP is typically also eligible for RNP APH, RNP RNAV1, RNP RNAV2, RNP4, and RNP RNAV10, but ARNP eligibility does not automatically confer RNP AR eligibility. RNP1 requires a lateral accuracy value of 1 for arrival, departure, and the initial intermediate approach phase on conventional procedures with PBN segments. RF turn capability is optional. RNP2 applies to domestic and oceanic remote operations with a lateral accuracy value of 2. RNP4 applies to oceanic remote operations with a lateral accuracy value of 4 and automatically confers RNP10 eligibility.
RNP10 applies to oceanic remote operations with a lateral accuracy of 10. Any aircraft eligible for RNP4 is automatically qualified for RNP10. RNAV10. RNP 0.3 requires a lateral accuracy value of 0.3% for all authorized phases of flight except oceanic, remote, or final approach, and initially applies only to rotorcraft operations. Depiction of PBN requirements. In the U.S., a procedure's PBN requirements are displayed in a standardized PBN box on the chart, listing the procedure's nav spec and, if required, specific sensors or infrastructure needed, additional or advanced functional requirements, the minimum RNP value, and any amplifying remarks. Items in the PBN box are required to fly the procedure's PBN elements. A separate equipment requirements box lists ground-based equipment and/or airport-specific requirements. Where both exist, the PBN box is listed first. 3. Other RNP applications outside the U.S.
The FAA and ICAO member states have led initiatives implementing the RNP concept for oceanic operations. For example, RNP-10 routes have been established in the Northern Pacific, increasing capacity and efficiency by reducing the distance between tracks to 50 nautical miles. 4. Aircraft and airborne equipment eligibility for RNP operations. Aircraft eligible for RNP operations will have an appropriate entry, including special conditions and limitations, in its Aircraft Flight Manual, Avionics Manual, or a supplement. Operators of aircraft without specific RNP eligibility statements may be issued operational approval, including special conditions and limitations for specific RNP eligibilities. Note: some airborne systems use estimated position uncertainty, also called actual navigation performance or estimated position error, as a measure of current estimated navigational performance. TBL 121, U.S. Standard RNP levels. Practical application for GA pilots before flying an RNAV or RF turn procedure. Check your specific aircraft's AFM or avionics supplement for RNP AR eligibility. Being cleared for RNP APH does not automatically mean you're authorized for RNP AR, even in the same airplane. Attempt to make a joke relevant to the material. RNP 0.3 walked into a job interview and said, "I can stay within 0.3 of a mile, 95% of the time." RNP 10 said, "I'll take the oceanic job." Nobody's checking that closely out there. B. Why did the pilot bring a magnifying glass to check RNP AR eligibility? Because the difference between qualifying and not qualifying is written in very fine print in the AFM. C. An aircraft eligible for ARNP tried to sneak into an RNP AR approach without authorization. The gate agent said, "Nice try, but ARNP doesn't get you AR privileges." 1, 2, 3. Use of suitable area navigation systems on conventional procedures and routes. The next section is use of suitable RNAV systems on conventional procedures and routes. Here's a summary from AMP Aviation. This is the FAA's permission slip to use your GPS as a stand-in for a broken or absent VOR, DME, or NDB, with some very specific fine print about what that permission does and doesn't cover. 1. Discussion. This paragraph sets forth policy while providing operational and airworthiness guidance regarding the suitability and use of RNAV systems when operating on or transitioning to conventional, non-RNAV routes and procedures within the U.S. National Airspace System. A suitable RNAV system may be used as a substitute means of navigation when a VOR, DME, TACAN, VORTAC, VOR, DME, NDB, or compass locator facility is out of service, or when the aircraft is not equipped with ADF or DME. For example, a pilot may hold over an out-of-service NDB if equipped with a suitable RNAV system. A suitable RNAV system may also be used as an alternate means of navigation when the underlying facility is operational and the aircraft has compatible operational navigation equipment. For example, a pilot may fly a procedure based on an operational VOR using the RNAV system without monitoring the VOR. Note: pilots planning to use their RNAV system as a substitute means of navigation guidance in lieu of an out-of-service NAVAID may need to advise ATC of this intent and capability. The navigation database should be current for the duration of the flight. If an amended chart is published for a procedure, or the procedure's amendment date shown on the chart is on or after the expiration date of the database, the operator must not use the database to conduct the operation. 2. Types of RNAV systems that qualify as a suitable RNAV system. When installed and operated in accordance with applicable requirements, a suitable RNAV system includes an RNAV system with TSO C129/C145/C146 equipment, installed per AC 2138 and authorized for IFR en route and terminal operations, or an RNAV system with DME/IRU inputs compliant with AC 9100A for RNAV routes. Note: approved RNAV systems using DME/IRU without GPS Voyage position input may only be used as a substitute means of navigation when specifically authorized by NOTAM or other FAA guidance for a specific procedure. 3. Uses of suitable RNAV systems. Subject to operating requirements, operators may use a suitable RNAV system to determine aircraft position relative to or distance from a VOR, TACAN, NDB, compass locator, or DME fix, or a named fix defined by a VOR radial, TACAN course, NDB bearing, or compass locator bearing intersecting a VOR localizer course, navigate to or from a VOR, TACAN, NDB, or compass locator, hold over a VOR, TACAN, NDB, compass locator, or DME fix, or fly an arc based upon DME. These allowances apply even when a facility is identified as required on a procedure, but do not include lateral navigation on localizer-based courses without reference to raw localizer data, and cannot be used for navigation on procedures identified as not authorized without exception by a NOTAM. Pilots may not substitute for the nav aid providing lateral guidance for the final approach segment. However, use of a suitable RNAV system to navigate the final approach segment of a procedure based on VOR, TACAN, or NDB signal is allowable provided the underlying nav aid remains operational and monitored for final segment course alignment. 4. Alternate airport considerations. For flight planning purposes, any required alternate airport must have an available instrument approach procedure that does not require the use of GPS, including a conventional approach at the alternate using a GPS-based substitute means of navigation for an out-of-service VOR supporting, for example, an ILS missed approach procedure. This restriction does not apply to RNAV systems using TSOC 145/C146 OEAS equipment, TSOC 1290, TSOC 1960, users with fault detection and exclusion capability who perform a pre-flight rain prediction and have the required knowledge training. Approval may file based on a GPS-based instrument approach procedure at either the destination or the alternate airport, but not both. If those conditions cannot be met, the required alternate must have an approved instrument approach procedure other than GPS that is anticipated to be operational and available at the estimated time of arrival. Practical application for GA pilots if you plan to hold over or shoot the final segment of an out-of-service VOR or NDB using your GPS as a substitute. Tell ATC that's your intent. Don't assume the controller already knows your equipment can do it. Attempt to make a joke relevant to the material. A, an out-of-service NDB and a GPS receiver meet at a holding fix. The NDB says, "I can't help you today." The GPS says, "That's fine. I brought a note from the FAA saying I can cover your shift." B, why don't pilots use a GPS substitute for the final approach and evade? Because the FAA said, you can borrow the car, just not while it's parked in the garage. The underlying facility still has to be operating and monitored. C, a suitable RNA system tried to fly a procedure marked NENA by NOTAM. The procedure said, suitable or not, I'm closed for business. 124, recognizing, mitigating, and adapting to GPS jamming and or spoofing. The next section is recognizing, mitigating, and adapting to GPS jamming and or spoofing. Here's a summary from AMP Aviation. GPS signals are whisper quiet by the time they reach your antenna, which makes them easy to drown out or fake. This paragraph is the FAA's field guide to noticing when that's happening to you. 1. The low-strength data transmission signals from GPS satellites are vulnerable to various anomalies that can significantly reduce the reliability of the navigation signal. The GPS signal is vulnerable and has many uses in aviation. Therefore, pilots must place additional emphasis on closely monitoring aircraft equipment performance for any anomalies and promptly inform air traffic control of any apparent GPS degradation. Pilots should also be prepared to operate without GPS navigation systems. 2. GPS signals are vulnerable to intentional and unintentional interference from a wide variety of sources, including radars, microwave links, ionosphere effects, solar activity, multipath error, satellite communications, GPS repeaters, and even some systems on board the aircraft. Of greater and growing concern is the intentional and unauthorized interference of GPS signals by persons using jammers or spoofers to disrupt air navigation by interfering with the reception of valid satellite signals. Note, the U.S. government regularly conducts GPS tests, training activities, and exercises that interfere with GPS signals. These events are geographically limited, coordinated, scheduled, and advertised via GPS and/or WAAS NOTAMs, and operators should always check for these NOTAMs for their route of flight. 3. Manufacturers, operators, and air traffic controllers should be aware of the general impacts of GPS jamming and/or spoofing, which include, but are not limited to, inability to use GPS for navigation, inability to use hybrid GPS inertial systems for navigation, loss of or degraded PBN capability, unreliable triggering of terrain awareness and warning systems, inaccurate aircraft position on navigation displays, loss of or erroneous ADS-B outputs, unexpected effects when navigating with conventional navaids, unanticipated position, dependent flight management system effects, such as an erroneous insufficient fuel indication, failure or degradation of air traffic management infrastructure reliant on GPS, potentially resulting in airspace infringements or route deviations, failure of or erroneous aircraft clocks, resulting in inability to log on to controller-pilot data link communications, and erroneous wind and ground speed indications. 4. When flying IFR, pilots should have additional navigation equipment for their intended route to cross-check their position. Routine checks of position against VOR or DME information, for example, could help detect a compromised GPS signal. Pilots transitioning to VOR navigation in response to GPS anomalies should refer to the Chart Supplement US to identify airports with available conventional approaches associated with the VOR Minimum Operational Network Program. 5. Prior to departure, the FAA recommends operators be aware of potential risk locations, check for any relevant NOTAMs, plan fuel contingencies, plan to use conventional nav aids and appropriate arrival approach procedures at the destination, and follow the detailed guidance from the respective original equipment manufacturer. 6. During flight, the FAA recommends operators be vigilant for any indication that the aircraft's GPS is disrupted, verifying position by conventional nav aids when available. Indications of jamming and/or spoofing may include changes in actual navigation performance, aircraft clock changes, incorrect FMS position, a large shift in displayed GPS position, PFD-ND warnings about position error or other aircraft reporting clock issues, position errors, or requesting vectors. Operators should assess operational risks and limitations linked to loss of GPS capability, ensure nav aids critical to the intended route approach are available, remain prepared to revert to conventional instrument flight procedures, and promptly notify ATC if they experience GPS anomalies. 7. Post-flight, the FAA recommends operators document any GPS jamming and/or spoofing in the maintenance log to ensure all faults are cleared, and file a detailed report at the FAA's GPS anomaly reporting site. Practical application for GA pilots: before any IFR flight through a region with known or historical GPS interference, brief yourself on which conventional nav aids back up your route and destination, and be ready to ask ATC for a heading or a non-GPS approach the moment your position display looks even slightly off. Relevant NTSB update: on May 13th to July 14th, 2026, a Beech C-90 King Air operating a Part 135 air ambulance flight from Roswell to Ruidoso, New Mexico, crashed while military GPS jamming activity was active along the route. The crew reported losing GPS capability shortly after departure and requested heading guidance from ATC, then switched their planned approach from RNAV to the ILS after losing satellite-based navigation. Other aircraft in the area reported GPS disruptions during the same period. Both pilots and 2 flight nurses were killed. As of this writing, the NTSB has issued only a preliminary report and has not yet determined a probable cause, so no conclusion should be drawn about what caused the accident. It's included here because it's a current real-world illustration of exactly the GPS jamming scenario this paragraph describes, not as a finished case study. Attempt to make a joke relevant to the material. A. GPS spoofing's favorite trick: telling your airplane it's somewhere it's absolutely not, with complete and total confidence, basically the avionics version of a bad GPS voice giving you directions into a lake. B. Why did the pilot start cross-checking VOR and DME again? Because when the GPS said, "You have arrived," they were pretty sure they hadn't. C. A jammer and a spoofer walk into a cockpit. The jammer just makes noise. The spoofer tells you a very convincing, very wrong story about where you are.